Now, these ones are kind of interesting. We've got this function y, which was explicitly solved for x. In this Leibniz notation here, this means the derivative. I have found the derivative of y and got sine of x. But if I plug in 0 into the function, I get 5. Okay? So what does that give us? Well, what do we know? Well, then y would be the negative cosine of x plus some constant. Now, that point there, 0, 5, is going to give us the exact value of the constant. So we know precisely what function started this whole mess. So we're going to think about the fact that 0, 5 is a point for this function. And we're going to plug in 0, 5, and we're going to find the c. So our y value is 5. Our x value is 0. The cosine of 0 is 1. We're going to add 1 to both sides, and we find that our c value is 6. To solve then for the original function precisely, we could say that y is negative cosine of x plus 6. Not only does that have a derivative of sine of x, so you have to, how can you check it? Well, if you take the derivative, you should get sine of x. But also, in the original function, if I plug in 0, I should get out 5. And if you plug 0 into this one, you would get out 5. So that is how you do a problem where we know some information about the derivative and a point for the original, and how we work our way backwards to find the exact function that we started with. So that's example 453. Let's take a look at 454. A car is traveling at a rate of 88 feet per second when the brakes are applied. The car begins decelerating at a constant rate of 15 feet per second squared. How many seconds elapse before the car stops? Okay, so there's a few pieces of information that I want to help you practice pulling out of the problem. Okay, so let's look at what we know. I'm going to call it the initial velocity. Let's call it v sub 0 is 88 feet per second. Okay. My initial acceleration is decelerating, so it's slowing down at a rate of negative 15 feet per second squared. Okay. Now, let me remind you how things worked about velocity and all that stuff. The position function, if I take its derivative, I get the velocity. If I take its derivative again, or the derivative of the velocity, I get the acceleration. So what we're going to have to do in this is we're going to have to go backwards. So we're going to go backwards. Okay, so this is kind of, in a way, similar to what we just know. So it says, how many seconds elapse before the car stops? So let's take our acceleration information and let's go backwards. Well, the velocity equation would have to be negative 15t, or we're looking at how long it takes, how many seconds it takes for it to stop, and plus some initial velocity, which will always be our constant. And in this particular point, we know that we've got the 88. So our velocity equation is negative 15t plus 88. Okay, now let's think about what's happening. They want to know, when does the car stop? The car will stop when the velocity equals 0. So this question right here is really velocity equals 0. So when does this equal 0? That's pretty easy. We're just going to go So we're going to go velocity negative 15t plus 88 equals 0. And we're going to solve it. Negative 15t equals negative 88. T equals 88 over 15. And this is a time problem, so I would say that actually getting an actual answer is probably good. And 88 divided by 15 is about 5.9 seconds. So it takes about 5.9 seconds for it to stop. Okay, so then let's look at part B. How far does the car travel during that time? Okay, so let's just take a look at now our position function. Our position function tells us the distance that it's traveling. So our position function is going to have to go backwards one more time. So that's going to be negative 15t squared divided by 2 plus 88t plus some initial position. And we're going to think of that initial position as when the brake's applied. And that initial position, we're going to call that time the 0 point. So we don't need anything because that's really going to be plus 0. Okay. So it says, how far does the car travel during that time? Okay. So we know at 5.9 seconds what's happening. So if we think about the equation, and I'm going to put x's in just so that Decimus knows what I'm talking about, of negative 15 divided by 2 x squared and plus 88x. And I am going to look at it just between 0 and 5.9. Okay. There we go. Do you see how all of it is positive? Okay. So it is traveling from a position of 0. That's, we're considering our starting point. And then that value at the top is right at the point that it's going to stop, 5.9. So now if you go and look, so our position at 0 should be 0. So let's just plug in 5.9 to see how far it goes. Negative 5/2 times 5.9 squared plus 88 times 5.9. So at that spot, you'll notice all of our units are feet, because I didn't use the 60 miles per hour, I used 88 feet per second, is 258.125 feet. Okay, so we can find, if given the acceleration, sometimes we need an initial velocity or an initial position to fill these little spots right here. But otherwise, we could actually find a lot of information about something. If we just know its acceleration, we can start working our way backwards.